In 2023, the global community launched over 3,000 objects into space, a 24% jump from the previous year. But this rapid expansion hits a strict logistical barrier. Hauling heavy, essential resources like water and metal up and out of Earth's deep gravity well costs millions of dollars per trip, making long-term exploration prohibitively expensive. To solve this, engineers are developing in-situ resource extraction. Instead of bringing everything from Earth, companies plan to mine near-Earth asteroids, specifically targeting water ice that can be processed directly into hydrogen and oxygen rocket propellant. Overcoming this reliance on Earth-based supply drops is the primary requirement for humanity to build a self-sustaining infrastructure in orbit. The math behind this operation is already changing. This chart tracks launch costs since 2010, showing a 90% drop to reach orbit. With transit costs slashed, analysts project the space mining market will scale from its pre-commercial phase into a $2.7 trillion economy by 2050. Reaching an asteroid is only half the problem. Once there, standard wheeled rovers are practically useless. In near-zero gravity, driving over treacherous rocky terrain causes a wheeled vehicle to lose traction and float away. Unlocking this multi-trillion-dollar market requires a total reinvention of how machines move and anchor themselves in microgravity. The solution lies in biomimetics. Companies like the UK's Asteroid Mining Corporation are developing specialized walkers to replace wheeled rovers, notably the SCAR-E prototype. Weighing just 20 kilograms, this modular robot trades traditional treads for 6 highly flexible, articulated legs. These limbs allow the probe to securely scale vertical walls, inspect steep lunar craters, and navigate extreme environments without losing its grip. Trading wheels for gripping claws solves the mobility crisis of low-gravity prospecting, allowing these machines to safely maneuver right up to mineral deposits for close-range detection. Once the robot finds a deposit, it faces a strict physics problem. According to Newton's third law, every action has an equal and opposite reaction. If a machine pushes down to dig into rock in low gravity, the force simply pushes the entire spacecraft backward into the void. This diagram from NASA's Robotic Asteroid Prospector project shows how spider robots counter this force. They use deep, fluted augers mounted at the ends of their legs to actively drill into the surface. By attaching these anchors at oblique angles, the system generates a net force along the surface. This lateral and downward bracing force pulls the spacecraft tightly against the asteroid. Securely clamped to the rock, the machines can begin extraction. They deploy mechanical scoops for loose material, use concentrated lasers to vaporize and collect metals, or even wrap entire small asteroids in inflatable capture backs. Mastering these low-gravity anchoring mechanisms allows engineers to convert floating, hazardous debris into stable industrial worksites. Pulling a few ounces of metal from a rock is a scientific achievement. To build a true industry, extraction must run continuously and at scale. Companies like Offworld are writing autonomous software systems that allow robotic swarms to coordinate their own surveying and mining. This removes the massive overhead of keeping 24/7 human ground control teams on the clock. Hardware is also becoming more efficient. This proposed modular spacecraft architecture uses a single primary structural truss to carry interchangeable propellant tanks and dual solar concentrators, stripping away the need to design unique ships for every mission. Replacing human remote control with autonomous swarms, paired with adaptable hardware, creates the exact mathematical formula needed to make space mining profitable over the long term. These engineering breakthroughs arrive exactly as global demand spikes for rare earth elements and in-orbit manufacturing materials, accelerating commercial timelines toward the early 2030s. This chart illustrates the international race for resource capture. India leads with a projected 36% compound annual growth rate, driven by its expanding mission count. The margins are tight. China follows at 34%, the US at 32%, alongside European aerospace hubs like Germany. National governments and state-backed institutions are now competing in a strategic race for dominance over extraterrestrial resource streams. Practical engineering and robust legal frameworks have pulled asteroid mining out of the realm of speculation and into the commercial sector. Plunging launch costs and the development of highly autonomous, multi-legged robotic systems have addressed the core logistical hurdles of orbital extraction. Right now, engineers are assembling the foundation of the first extraterrestrial supply chain, a logistics network designed to fuel a multiplanetary economy.